equations. They have so much structure relating to so many fields of mathematics. And so I want to start the way Sasha would like, which is that we can consider Gauss hypergeometric function. And so Gauss discovered relations between this function and function where we shift one of the parameters by one, for example, a plus 1 bc. So one can rewrite functions like this in terms of functions like this. And I want to talk about some generalization of this and what we can use it for. So this is based on my work with Varchenko, 2 papers, which are in written last year. And so it's a theory of periodic pencils of differential equations depending on parameters, such that if you shift parameter by an integer, you get an equivalent equation. So let me start with general setup. So for me, my equations will be on a smooth variety X over some field K. And this variety usually will be just a vector space or maybe open set in a vector space. And passing from variety to open set will not, it won't matter because actually this theory doesn't change when you pass to an open set localization. So in particular, I want the equation to be a connection on some vector bundle, but I will consider trivial vector bundle because any vector bundle is trivial when localized to an open set. And then I make a definition, polynomial family of flat connections. Well, it's just a connection that depends polynomially on some parameters. So this means that it's a family of connections, nabla of S, which is d minus b of S1 through Sn. S1 through Sn are parameters, like here it would be A, B, and C. And B is a one form, as usual, with coefficients and endomorphisms of this space V. And it should depend polynomially in S1, Sn. So flatness of this connection is just the Maurer-Cartan equation. And here is a definition that will be important, that this is called a pencil if it linearly depends on S, linearly homogeneously. So B equals to S1 B1 plus so on plus Sn Bn. So if you have a pencil, then flatness condition is written as dBi equals to 0 and commutator of Bi Bj equals to 0. But in the one-dimensional case, these conditions are vacuous. And this theory is going to be interesting even in the one-dimensional case. For example, of a pencil, you should, I will give an example, but until we reach this example, you can think, for example, of Nizhny-Zamolodchikov or Dunkel differential equations, where the right-hand side depends linearly on some parameter h bar. And here is the main definition. The main definition says the following. A family nabla of S is said to be periodic if there exist shift operators, aj of S, and these operators are matrices, invertible matrices, so elements of GLV, with coefficients in the ring of functions on X over the field of functions of S, rational functions of S. So they can have poles with respect to S, but not with respect to X. And they will, in fact, have to have poles to have interesting question.
Yes. So you only consider order one polynomials, right?
No, I will consider general, but the most powerful results will be for order one. Unfortunately, this is used in the proof, which is a big problem, for example, for extension to Q difference equations, where you don't have in the examples with degree one polynomials, and so or don't have many. So this is a kind of bug in this theory, which I don't know still how to remove. But luckily for differential equations, a lot of examples have degree one polynomials, and so it works. So, and the condition is that this AJ of S should intertwine the connection nabla of S and connection nabla of S plus EJ, which means that I shift the J's variable by one and keep all others fixed, like here. And so it turns out that such pencils have a some remarkable properties. So in this example, for example, you can write it as a pencil, and this has these Gauss relations, which allow you to connect this equation for this function and equation for this function. And so it turns out that these pencils, on one hand, have many remarkable properties, and on the other hand, there are many interesting examples. So let me start with an example, actually, which is a little bit lower. I added it today because I felt that okay, starting with an explicit example is nice. And so this is the hypergeometric pencil. So this is the most basic non-trivial example. And the hypergeometric function corresponds to this example where the number r is equal to 3, which is the simplest non-trivial case. So the differential equation is with respect to a vector I1 through IR. And it's on the space X. Okay, this is a fire alarm, right?
That's a fire truck. Training for fire alarm.
Okay.
But there will be one.
And the equation lives also on the r-dimensional space with diagonals removed. And it has the form of Knyzhnik-Zamolodchikov equation. This is the most basic example of Knyzhnik-Zamolodchikov equation. So we have parameters S1 through SR.
This is one.
This is just a test.
Yes, unlike Israel, where I was yesterday, this is just a test. There it was a real alarm where we had to hide, but we don't have to hide here.
Not yet.
Okay. So we have these differential equations, dij over dxi equals to si times ii minus ij over xi minus xj. And so then the basic solutions of these equations are of the following form. So ij, they're parameterized by cycles gamma x inside inside of configuration space of points on the complex plane with points xi removed. And j's coordinate of this solution is the integral over this cycle of so it's the integral over the cycle of this product times dt over t minus zj. And these integrals satisfy the equation, the sum over k of xk, sk times ik equals to 0, because then it's a residue calculation. Basically, if I take the sum with sk, this form is going to be exact. And so not residue, it's just a statement that this form is exact when I take the sum with coefficients sk. And gamma k is a cycle, for example. So the basic cycles are these Pochhammer loops, which is a commutator in a fundamental group of the loop around xi and loop around xi plus 1. And then there is also a solution where all i's are 1. That's a trivial solution. And these trivial solutions and the non-trivial solutions given by the formulas above form a basis. And then one can show that the shift operators, which transform variables si to si plus 1 or sk to sk plus 1 and fixes the other ones, is given by this formula. So this matrix AK, so ei, j are elementary matrices, and so it acts separately on the space of solutions of this equation, sum sk ik equals to 0, and on the vector 1, those are invariant subspaces, and on each of them it acts as written here. Okay, and so this is basically a way to write down Gauss relations, but it is for function fn n minus 1 in general. Okay, so now I go back to this story, and
Sorry, Pasha, you said that it shouldn't have poles in X, but in your example, it has poles in X.
no. It's variety. No, so it should not have mixed poles with X and S, but variety X is in this case not the affine space, but affine space with removed diagonals.
Thanks.
So the differential equation is defined on the complement of diagonals, and the shift operators don't have poles on the complement of diagonals. They only have poles on the diagonals. Okay, so let me start now. So I start with the theory of complex numbers, and this will involve some complex analysis. And then I will pass to positive characteristic, which will use some algebraic geometry, number theory, and so on. So, so the first case is complex numbers. And I fix, in this case, I can fix a base point on my variety. Let's say it's connected. And then I get the monodromy representation from pi 1 of x with base point x0 into the general linear group. So this is the monodromy representation. And I make a definition that this family has periodic monodromy if for every k, the representation rho s corresponding to parameters s and rho of s plus ej are isomorphic. Well, it is too strong to require that they are isomorphic for all s. That never happens. So we should require that they are isomorphic for many s. In fact, usually they are isomorphic for almost all s, but all I need for the proof that they are isomorphic on what I call a large set. A large set will be any subset of Cn, which is not contained in a countable union of proper analytic subsets. So it's a much weaker than saying all, almost all, but actually it happens usually for all. And here is the first theorem. So the first theorem says that a pencil nabla of S has periodic monodromy if and only if its monodromy representation is defined over a finite Galois extension of the field of rational functions of the exponential variables qj equals to e to the 2 pi I sj. Actually, in all examples, it's defined over this field itself, but for the proof, I need to make an algebraic extension, which doesn't really create any problem. So here is a sketch of proof. So I should say that this is a rare property. If I just write in the differential equation d f over dz equals to s times a of z times f, if this equation has a rank more than 1, you should not expect that this is going to monodromy is going to depend on e to the 2 pi I s. It will be some analytic function of s, but it will not in general depend on e to the 2 pi I. So the sketch of proof is that, well, so we have a holomorphic map from Cn to, I mean, it won't depend on e to the 2 pi s, and in fact, it won't depend, it won't be a rational function in any sense. So you won't be able to compute it in elementary terms in any basis. But here it's different. So we have a map from C to the N to the space of representations of the fundamental group. And well, this is not a variety, this is a stack, which means that you have to be careful, but let me sweep it under the rug so you can deal with this because you only care somehow about generic pieces of some strata. And this map is periodic with period z to the n because our pencil is periodic. So therefore, we get a holomorphic map from C star to the n into Cn modulo z to the n into this home space modulo GLV. And since nabla is a pencil, which means it linearly depends on S. So if you have a differential equation linearly depending on S, such as df over dz is, for example, S times A over df, then monodromy is going to be exponentially bounded. Monodromy is going to be along a fixed curve, is going to be bounded by an exponential function of S. So, but that means that if I rewrite it in terms of exponential coordinates, because we have a function on Cn mod z to the n, then it will be polynomial growth at infinity, because we write exponential function which is exponentially bounded in terms of exponential coordinates. And so this rho bar, which goes from C star to the n, has polynomial growth. And so this means that it's a regular algebraic map. In complex analysis, if you have a map that has polynomial growth at infinity, it's a regular algebraic map. And now what I would like to have is I would like to have a map to the home space itself, not home space modulo GLV. And for this, I need to make this extension, because in algebraic geometry, if I have a map from a scheme to a quotient, this doesn't mean that I can lift it to a map to the so if I have a map from a scheme to a quotient x mod g, this doesn't mean that I can lift it to a map from a scheme S to X, but I can lift it after taking a finite cover of S. And that's exactly what what the Étale slice theorem says, and that's exactly what I need to prove this theorem. Okay, so any questions?
Well, maybe silly question. Well, you say it's polynomial, but why it is polynomial? It could be probably some fractional power. No, you know, because you have exponential. If it is integer, that will be polynomial. But
no, it's honestly periodic. Like suppose you have one variable S, so then it's a function on C star. Honest regular function.
periodic. Okay.
Yeah. So other questions? Okay. So now the next theorem is the following. It says that the family nabla of S with regular singularities, which means first order poles in some basis, in some presentation, is periodic if and only if it has periodic monodromy. And why is this theorem useful, first of all? Well, because I gave you an example with hypergeometric functions when we could explicitly calculate these shift operators. But very often, it is very difficult to calculate these operators, even though they exist. On the other hand, just the mere existence of these operators has some consequences for p-curvature and other things. So sometimes you want to be able to show that these operators exist without actually computing them. And that's exactly what this is useful for. So let me explain the proof. So again, in one direction, this is trivial. If connection is periodic, then it has periodic monodromy, because if equations for S and S plus 1 are equivalent, they have the same monodromy up to isomorphism. But the converse follows as follows. So regular singularities and periodic monodromy by Riemann-Hilbert correspondence implies that the differential equations are also isomorphic, not just monodromy, but the differential equations themselves are isomorphic when you shift S by EJ for individual values of S for many individual S, for a large set of individual S. And then this is because Riemann-Hilbert correspondence says that there is an equivalence of categories between connections with regular singularities and representations of the fundamental group. And now some abstract nonsense, namely Chevalier elimination of quantifiers, implies that if this isomorphism exists pointwise for individual S, then there exists actually a rational function of S that evaluates to isomorphisms at almost every S. And this allows us to give many examples of periodic pencils to show that there are actually many examples. So I gave you already the example of hypergeometric pencil, but a more general example is the Knizhnik-Zamolodchikov of connections. So here we are thrown in the realm of representation theory. So we have a simple finite dimensional Lie algebra. Cartan subalgebra, and we have weights lambda 1 through lambda r. And then we have some fixed element of the root lattice, which is positive. I call it beta. And m lambda here, so I denote by m lambda the Fermat module over the Lie algebra with highest weight lambda. And then we consider the space V, which is the tensor product of these Fermat modules, and weight subspace there of this weight, lambda, which is highest weight minus beta. And then one can show that this space only depends on beta, does not depend on lambda 1 through lambda r. Using, we can identify it with some weight space in the tensor product of universal enveloping algebras of negative nilpotent subalgebra. And then if you, in the Knizhnik-Zamolodchikov connection, is the connection on this configuration space, C R minus the diagonals, given by the standard formula, nabla kz equals to D minus H bar times the summation I equals 1 to R summation over J, omega ij over Zi minus Zj dzi, where omega is Casimir tensor for G. And this connection is flat. It's well known and easy to check, but it depends not only on the parameter H, but actually also on the parameters lambda. And if you rewrite it in terms of parameters H and H lambda, then it is actually a pencil. Everything is linear, homogeneous with respect to S. And so there are many parameters here, 1 plus R times rank G. And then there is a proposition that this pencil is periodic up to rescaling S by 2 or something like that. And the reason is that it has regular singularities. This is actually obvious here, first order poles, and also at infinity, it is easy to check that that property is satisfied. And then by theorem 2, it's enough to check that it has periodic monodromy. And monodromy of Knizhnik-Zamolodchikov equation was computed by Kohn, Drinfeld, and it is given by our matrices of the quantum group Q of G. And this monodromy then depends on e to the pi I H bar in the simply laced case, and which is called Q, and Q to the lambda I. And this implies that there is periodic monodromy. Monodromy is expressed in terms of exponential variables. And the example with hypergeometric pencil is the simplest case when our Lie algebra is SL2 and beta is equal to 2, which is the simple root for SL2. And there are many generalizations of this. You can consider Knyzhnik-Zamolodchikov for Katz-Moody algebras, for Lie superalgebras, for trigonometric Knyzhnik-Zamolodchikov equations. You can consider elliptic Knyzhnik-Zamolodchikov equations. And you can consider Knyzhnik-Zamolodchikov in the line category, and so on. The second example is also comes from representation theory, and this is so-called Casimir connections, which were introduced by De Concini in 1990s, and then studied intensively by Valerio Toledano Larreda and his collaborators. This is a connection on the variety X, which is regular part of Cartan subalgebra of the simple Lie algebra. And fiber is the space like before, but only for one factor, m lambda of lambda minus beta. And the connection has the form E minus H times the sum of positive roots, E alpha F alpha plus F alpha E alpha over 2, which is essentially the Casimir of SL2 without the Cartan part, which is not important here, and multiplied by D alpha over alpha. And E alpha and F alpha are root elements of our Lie algebra G. And so this connection is flat, and it forms a pencil with parameters lambda and h and h lambda, and it's periodic up to rescaling s. So the proof is of similar kind. This has regular singularities, so we only need to show that it has periodic monodromy. And this follows from a theorem of Appel and Toledano Larreda that monodromy of this connection is given by the quantum Y group of the quantum group Q of G. And this also expresses in terms of exponential variables. And then this generalizes to Casimir connections for Katz-Moody algebra, for trigonometric Casimir connections, and so on. And the final group of examples is the Dunkel connections. In this case, this is maybe the simplest to state. So we have W, which is a finite Y group with a reflection representation H. We have V, which is a representation of Y group. And the Dunkel connection is the connection on the regular part of the reflection representation, with fiber being this representation of the Y group. And the Dunkel connection is number equals to D minus H times the sum over the reflections, S times D alpha S over alpha S, where alpha S is the root corresponding to S. So there is one parameter H in this case, and this is a flat pencil. So the claim is that this is a periodic pencil. So this means that the equation for parameter H and H plus 1 are equivalent. But it is not easy to write down this equivalence, although this equivalence is actually, in this case, can be computed explicitly. And this is the so-called Obdam shift operator. And so, but you can prove the fact that this is a periodic pencil even without using Obdam's shift operator, by using the fact that this has regular singularities and monodromy is given by the Hecke algebra. So in this case, it's very easy to show that monodromy, which is representation of the braid group, is given by the Hecke algebra. And the parameter of the Hecke algebra is exponential of 2 pi I h. And this implies the fact that this falls into our and there are generalizations which are Dunkel connections for complex reflection groups and trigonometric Dunkel connections. And then we consider the last example, which is comes from enumerative algebraic geometry. And this is a story about symplectic resolutions of singularities. So if I have a conical symplectic resolutions with finitely many torus fixed points, then this has this defines a so-called equivariant quantum connection. It's a connection living on the base, which is second cohomology of this resolution with values in C star. It's a torus with some divisor removed. At least it is conjectured to be that way, and it is so in many examples. And the fiber is the total cohomology of this resolution. And this is a flat family depending on the equivariant parameters of the torus. And it is known to be a pencil in a certain basis called the stable basis. And this is in fact a periodic pencil. And this can be proved directly by constructing these intertwiners, not computing them, but constructing them using enumerative algebraic geometry, so-called stable envelopes. And this was done by Etingof, Panharipande, Malriv, Braverman, and others. Okay, any questions?
So these operators in this case, they correspond to change of stable basis. Was the change
Yeah,
of
well, they're so-called shift operators. So they're defined by the Malikov book. Shift operators along the equivariant parameter.
You probably have to speak twice faster because you have just 5%.
Yeah, for some reason, this thing is not charging the battery. Usually these things charge the battery also. But it's not. Okay, no problem. So this means I will finish it.
It's a problem for us.
Ah, It's a different one. It may fit, but will it also project? No. Okay. All right. Well, then I maybe finish on the board. Okay. So what is so remarkable about these pens? Well, one of the important properties is that singularities of pencils occur on very restricted kinds of subsets, which are hyperplanes defined over the rational number, which means that the linear equation of the hyperplane has rational coefficients. Maybe the constant term, I don't know how to prove that it has rational coefficients, although this is very likely. Constant term is rational, but the linear terms, I can prove they are rational. And this echoes the fact that in representation theory, usually we are used to that our representations depend on some parameters. And then singularities, which is things like reducible representations and so on, occur on hyperplanes with rational coefficients. So one of the ways to explain it is that representation theory is, to any setting in representation theory, to most settings correspond to some sort of periodic pencil. So this agrees with Etingof's statement that symplectic resolutions are Lie algebras of 21st century. And so for periodic pencils, it turns out that this property is built into the theory that you automatically satisfy. And so let me explain how this can be proved. So what do I mean by singularities? For example, by singularities, I mean that the Bj, so I can consider for every j, the set Bj in Cn, which is the set of points where nabla of S is not isomorphic to nabla of S minus plus a j. And let's consider it Zariski closure. So Zariski closure actually is going to be some sort of algebraic variety, which is contained in the pole divisor of this AJ. So I said that AJ is going to have some poles, and in the pole divisor contained the singularity set. And the theorem is that every codimension 1 irreducible component of Bj bar is a hyperplane defined over Q up to shift. So this means that it cannot show the constant term defined over Q. And moreover, so if number of S is irreducible generically, then poles of the AJ, when it is projectivized, occur on such hyperplane. And one can prove similar results for other types of singularities, such as loci where this connection is not semi-simple, loci where endomorphism algebras jump, become bigger, and so on. So I will explain the proof of this theorem because it is kind of cool and simple. Well, it's not, it follows from something that's not so simple, but I will just state it. So we will use the following theorem, which is interesting in its own right, and which says that every periodic pencil automatically has regular singularities. So I said that periodic monodromy is equivalent to regular singularity is equivalent to being periodic pencil under the assumption of regular singularities, but in fact, regular singularities are automatic for periodic. And this echoes the fact that in enumerative algebraic geometry, when you consider these symplectic resolutions, then in all examples, the quantum connection of symplectic resolutions have regular singularities, but enumerative geometers don't know how to prove this in general. But this follows from this property. What's funny about this theorem is that the proof of this theorem uses reduction to positive characteristic. And this can be proved using p-curvature, which we'll explain below. Now the proof of the theorem 7 about singularities occurring on hyperplanes can be obtained from a nice elementary theorem, which everybody can understand. But it's a special case of theorem of X, which was one of the early results in applied model theory. It says that if you have, it's a theorem that exponential function is very transcendental. It says that if you have an algebraic hypersurface in Cn, such that when you exponentiate it, you also hit an algebraic hypersurface. Then this initial hypersurface has to be a hyperplane defined over Q up to shift. So it has a linear equation with rational coefficients. That's actually not so hard to prove. So I proved this on about a page, and then I discovered that this was a corollary of the theorem, so I didn't include my argument. But it is a nice middle difficulty exercise in complex analysis. And the proof of my theorem now is the following, that by this theorem, the theorem about exponentiating hypersurfaces and Riemann-Hilbert correspondence, I have so by theorem about periodic pencils, so that they have regular singularities, sorry, and Riemann-Hilbert correspondence. So that means I can apply Riemann-Hilbert correspondence, and the equivalence of differential equations is the same as equivalence of representations. And but singularities of differential equations occur in algebraic surfaces in variable S. And singularities of representations occur on algebraic surfaces in variables e to the 2 pi is. And that means that, in fact, in the variables S, it has to be a hyperplane defined over Q, and in exponential variables has to be a hypertorus. Okay, so this means that every irreducible component of this pole variety is hyperplane defined over Q up to shift. Let me now maybe switch to the board and start charging. Let's see if it works. Yeah, it works. Okay. Can we raise this screen? Okay, so now I want to talk about equations in characteristic P and later reductions of the previous equations from complex numbers to characteristic P. And so in characteristic P, so in characteristic 0 over C, every flat connection has a fundamental system of flat sections locally. And so it's true over C on a small disk around my point. And if I use formal power series, it's true over any field of characteristic 0. Just existence and uniqueness of solutions of differential equations. But in characteristic P, it's not true. So for example, I can consider equation in one variable, in which case the flatness condition is vacuums. So df over dt equals f. Dx equals f. So this equation is the simplest kind of differential equation that you can write. And the solution is well known up to scaling to be the sum from n equals 1, 0 to infinity, n x to the n over n factorial, which is the exponential series. But you see that there are these factorials in the denominator. So if you have a prime, there is a factorial divisible by this prime, and this series doesn't make sense. So this doesn't have any solution. And the reason for this is that besides usual curvature, which vanishes if your connection is flat, connections in characteristic P have an additional kind of curvature called p-curvature, and which occurs already in one variable. This p-curvature is the following thing. So see, if you have nabla I, which are covariant derivatives for your connection, let's say flat connection. So this means that they commute. Then you can define Ci, which is nabla I to the power P. And then the claim, they don't involve derivatives. That means that the Ci are just endomorphisms of V over the field of functions of. And so, well, I mean, you can check it, for example, for P equal 2. So if you have D plus A, and if you square that, that's going to be D squared plus AD plus DA plus A prime. And then you can compute DA plus A squared, I'm sorry. And then you can compute this DA, this is AD plus A prime. So this is going to be D squared plus 2AD plus A prime plus A squared. And this goes away because 2 equals to 0. And this is also goes away because second derivative of any polynomial in characteristic 2 is 0. Second derivative of x to the n is n times n minus 1, x to the n minus 2, and n times n minus 1 is always even. So what you are left with is this, and this is exactly this p-curvature. And it has no derivatives. So not only the largest term, d squared, or d to the p in general, goes away, but all the intermediate terms go away except for the last. And so, so these C's are just matrices, and they commute with each other. And they also commute with the connection. So this, in fact, implies this. And now if you have a solution, if you have nabla I f equals to 0, then this implies that nabla I to the p times f equals to 0, which means that ci f equals to 0. So in order to have a complete set of solutions, which means evaluation at the origin gives you a basis, you need ci equals to 0. Formal solutions is equivalent to saying that ci are 0 for all. And so in our example with the exponential series, the differential operator that we are dealing with is d minus 1. And if you raise it to power p, you obtain d to the p minus 1, which is minus 1. So this is the p curvature, and it is not equal to 0, and that's why we don't have solutions. So let's see. What is my probably gonna be enough for the rest of the talk. All right. The discussion of p-curvature. And here is a maybe main theorem which I want to describe. And the theorem says the following: that the p-curvature of if you have a periodic pencil, then you can say a lot about its p-curvature. Is at least about its eigenvalues. And this is already quite striking because in general, p-curvature, of course, for every p, we can compute it explicitly like we did in the case of p equals 2. But when p grows, the expression will get more and more complicated. And there is no pattern to it in general. And it has to be this way because, like I wrote here, we have Ci commutes with nabla J. So this means that nabla J restricts to the joint eigenspaces of Ci. So if you have a regular semi-simple, if the Ci's jointly are regular semi-simple, which happens generically, this means that my vector bundle splits in a direct sum of line bundles of the eigenbundles of Ci, and the connection preserves this decomposition. So this means that as soon as I know the p-curvature, I can basically diagonalize my connection and reduce it to a direct sum of one-dimensional connections. So essentially to solve the differential equation. Well, they don't have a solutions, but by solving, I mean reducing to one-dimensional connection. So that's why if I take a generic equation, such as, for example, Lemay equation for general parameter, and consider its p-curvature, it is a mess. There is no pattern to what you get. However, for hypergeometric equation, there is a nice description of the curvature, of the p-curvature, or rather its eigenvalues. And this is the case, in fact, for all periodic pencils. So let me talk about this. So the theorem says that a periodic pencil has p-curvature operator Ci, which are isospectral to the following thing. This is I take the B form, so we have B equals to the sum of Sj, Bj. Then I take a Frobenius twist, which means I take every matrix coefficient and raise it to power p. And then I multiply it by the Artin-Schreier function, S minus S to the p, of the parameter Sj. And so I take the sum, and then it's isospectral. So this means that for periodic pencils, so p-curvature is a kind, it's a way in algebraic geometry to take semi-classical limit, because differential operators d to the p and x to the p are central, and we basically reduce everything to polynomial algebra. And then p-curvature of a pencil. So there is a leading term with s to the p, and computing that leading term is basically the WKB approximation. So it's not surprising that it gives you this Frobenius twist, which is isospectral to b to the p. But what it says that WKB approximation is almost exact. It becomes exact if you replace s to the p by s to the p minus s for these pencils. And nothing like that holds for a generic differential equation. Here, isospectral means they have the same eigenvalues, the same joint eigenvalues. So, okay, so let me explain the proof because it is actually quite instructive. So the proof I will show is just in one variable case. In this case, we have a connection D minus SB, and C of S is the p curvature, which is just a matrix depending on S. And we have an isomorphism, nabla of S plus 1 is isomorphic to nabla of S because of the periodicity. So this means that the p curvature C of S plus 1 is conjugate to C of S, because they're just p powers, but they're just matrices. And this means that if I take the coefficient of characteristic polynomial of C of S, which is up to sine trace of wedge I of C of S, then bi of S plus 1 is equal to bi of S. Also, my p curvature is nabla of S to the p. And this is a polynomial in S of degree p, because nabla of S is a pencil. So this is where I use this linear condition. So this means that bi of S is a polynomial of S of degree p times I. But now this equation implies that periodic means it's a polynomial of the Artin-Schreier variable S to the minus S to the p. And this means that my bi of S, which is a polynomial of degree p times I, is in fact a polynomial of degree just I, but of the Artin-Schreier function S minus S to the p. And but also I know that p curvature at 0 equals to 0 because my connection is trivial at S equals to 0. And this means that bi of S is divisible by S to the I. So I have some polynomial beta I of degree I, and beta I of S minus S to the p is divisible by S to the I. But that can only mean one thing, that this polynomial is just a monomial with some coefficient beta 0. And now we can compute this coefficient beta 0 by actually doing the WKB approximation, which means we send S to infinity. Then the leading term is this minus of the p curvature is minus S to the p b to the p, and b to the p is isospectral to b1 because all eigenvalues of b to the p, and b to the p means I raise the matrix to power p, and b1 means that I raise every matrix coefficient to power p. But if I do that, in both cases, eigenvalues get raised to power p, and this means these are isospectral. Okay, so that's the proof. And this main theorem, it's pretty easy, but powerful. And in particular, a corollary of this is that if you have a periodic pencil and you take your parameter over field of characteristic P, and you have parameters which are in FP in the prime field, then, well, the theorem says that P curvature is isospectral to 0 because these Si minus Si to the P are equal to 0. And isospectral to 0 doesn't mean that it is 0, but it means that it's nilpotent. So we obtain that the P curvature is nilpotent at the points Si in FP. And also it gives important information about P curvature of connections of all these wonderful examples that we see from representation theory. we get these properties of the p-curvature, and nobody knew how to compute p-curvature of these equations. And so I should finish soon, but let me connect it to some old work of Nicholas Katz in 1970, around 1970. So he studied p-curvature systematically, and in particular, he defined a flat connection on a variety over algebraic numbers to be globally nilpotent if its reduction to characteristic p has nilpotent p-curvature for almost all p. And you have a different linear differential equation over algebraic numbers. You can take a sufficiently large prime, which does not occur in any of the denominators of coefficients, and reduce it mod p. And then you get a family of equations in characteristic p sufficiently large. And Katz said that it's globally nilpotent if the p curvature is nilpotent for almost all p. So this is an important notion. So I will explain in a second why. And the corollary we get is that the periodic pencil over q bar evaluated at rational values is globally nilpotent. Well, because I said that element of q bar, when you reduce it mod p, becomes an element of fp. An element of q. So it's evaluated at rational values of sj. They are a rational number, and you reduce it mod p, you obtain an element of fp, and we showed that there the p curvature is nilpotent. The reason this is important, one of the reasons, is that Katz proved that any globally nilpotent connection has regular singularities. This is a wonderful theorem. And this in particular proves that periodic pencils have regular singularities. Because it proves that periodic pencil has regular singularities at rational values of S. But being regular singularities is a condition that if it's satisfied on a dense set, it will be satisfied everywhere if you know that the poles are not moving. And the poles are actually not moving in this case. So I'll finish in 2 or 3 minutes. It's okay. So Katz theorem says the reason he actually was interested in is Hodge theory. So there is a notion of geometric flat connection. It's a flat connection that occurs as a direct summand in a Gauss-Manning connection for a family of varieties, projective cohomology of projective varieties. So if you have a family of projective varieties over some base, smooth projective variety, then cohomology bundle carries a flat connection, which is called the Gauss-Manning connection. And the Gauss-Manning connection, it's a regular connection with regular singularities. And this is an important class of connections. And they are semi-simple by the so-called decomposition theorem. And direct summands in them are called geometric connections. So that's a deep notion. Katz proved that a geometric connection is globally nilpotent. That's why this notion is important. And there is a converse statement, which is a conjecture that every globally nilpotent irreducible connection is geometric. It's very far from being proved. It's called the André-Bambieri-Dwork conjecture. And it's a generalization of the famous Grothendieck-Katz conjecture, which actually gave rise to the notion of p-curvature. So Grothendieck introduced p-curvature in the context of this conjecture. Of course, if you have a linear differential equation that has a basis of algebraic solutions, then its p-curvature has to be 0, because then it will have solutions modulo every sufficiently large prime. You can just take the power series and reduce it to algebraic function. Only finally many primes will go into the denominator of the power series. However, Grothendieck-Katz conjecture says that the converse is true. If your differential equation has vanishing p-curvature for almost all p, then it has algebraic fundamental solution. And that's very far from being proved, but it's a famous conjecture in arithmetic algebraic geometry. And so we know that our all periodic pencils are globally nilpotent. but they are whether they are geometric, it's an open question. So many of them are known to be geometric. Like Knizhnik-Zamolodchikov equation are geometric. Geometric means that solutions can be written by an integral formula. And integral formulas are known for Knizhnik-Zamolodchikov equation due to Shechtman and Varchenko. For Casimir connection due to Felder, Varchenko, Markov, Tarasov. But for Dunkel connection for exceptional groups, they are not known. So these are examples, and there are some other examples which are potential counterexamples to the Andrei Bombery dwarf conjecture. Hopefully they're not counterexamples. Hopefully conjecture is true, and we just don't know these formulas. But maybe one day we will discover integral formulas. This suggests if we believe this conjecture, we should believe the Dunkel equations that Heckman-Obdam hypergeometric functions, which are solutions of those equations, are indeed hypergeometric in the classical sense, that they have integral form. For 30 years or 40 years, people have been looking for these and have not found. All right, so maybe this is, maybe I should stop here. Thank you very much.
But you mentioned shift operator. I mean, these AJ operators which intertwine in the case of Dunkel connection, are they directly related? I mean, shift operators are for differential.
Yeah,
Rather than for matrix varied equations, for vector varied equations, right?
Yes, they are can be obtained from scalar value. So Obdam and Cayetano-Larreda have new work coming up where they study shift operators for matrix equations. But I think even shift operators for scalar equations are sufficient to show existence of these shift operators. It's not necessarily that it's very easy to write a formula, but you can at least prove that they exist. Of course, another proof, which is non-algebraic, comes from the fact that they define Hecke algebra representation.
So you said that Lamé equation or Hoyne equation, then they're of course not of that.
Not of that type, and elliptical Logerer-Moser is not of that type. The elliptic, so if you take Beliven's elliptic matrix and take the corresponding elliptic KZ equation, then it's okay because it doesn't have internal parameters. So the problem with the Lamé or Hoyne equation is that it has the internal parameters. Not everything is determined by the residues.
Accessory.
Or accessory parameters, right? So if you have accessory parameters, this is not going to happen. Because there is no shift operator that maps Lamé equation with parameter lambda to Lamé equation with parameter lambda plus 1. Even though integer values of lambda are nice, but if you have non-integer, for example, value, I don't know, pi and pi plus 1, there is no simple way to connect them. What is true is that the moduli of connections with the corresponding residue is the same. But then you have to say what is the map from this space to itself induced by the shift. And that map isn't something that you can easily understand.
Okay, so if there are no more questions, let's thank our people.
Нет, ну, может быть, и есть оператор на самом деле. Ваши же эти самые, которые периодически